All right, everybody. I finally got around to recording the video for section 10.5, which is our final section. I just wanted to get this to you before we get too far into the weekend. I want you to have something to study before we get to the last week. This is the kind of the final topic we're covering here. So far, actually, to rewind a little bit, we talked about constant coefficient homogeneous systems. Let me zoom in here. And the constant coefficient homogeneous systems that we dealt with at first, so that's what this number 1 is all about, is when we had linearly independent eigenvectors, not distinctly different eigenvalues. We don't need distinctly different eigenvalues to still get linearly independent eigenvectors. And I think I harped on that enough during the last lecture, but I still wanted to say it again. So you could have a 5x5 matrix that has, let's say, 3 distinctly different eigenvalues. Let's just say lambda sub 1 or lambda equals 1, 5, and 8. Let's say those are 3 of your distinctly different eigenvalues for a 5x5 matrix. And then you find out that 8 has multiplicity 3. That means when you took the determinant of a minus lambda I, you ended up with an equation that factored to the following. And remember, you set this equal to 0 to find out what your eigenvalues are. So you can see the eigenvalue of 8 has multiplicity 3. We actually call that the algebraic multiplicity of that eigenvalue, but you don't really need to know that unless you're in linear algebra. Now, each one of these eigenvalues, both 1 and 5, as well as lambda equals 8, each one of those will develop their own or provide their own distinctly different and linearly independent eigenvectors. So again, every single different eigenvalue will definitely give you a different linearly independent eigenvector. So I can guarantee I have at least 3 linearly independent eigenvectors from these 3 distinctly different eigenvalues. However, the real question is, can I get 2 more linearly independent eigenvectors from lambda equals 8, which has multiplicity 3? If I can, then we're in luck, right? And section, I forget what section this was, section 10.3 really started us off on that idea that, hey, we're going to go ahead and assume that we're going to give you matrices that have n linearly independent eigenvectors. But then in 10.4, which is titled Constant Coefficient Homogeneous Systems Part 2, we ran into the case where, well, we have, let's just go back to that same example we were just talking about, 3 distinctly different eigenvalues, but unfortunately, the one that has multiplicity 3 does not generate 3 linearly independent eigenvectors. What do you do in that situation? And so we ended up finding out what we do in that situation, honestly. It was a recursive process, and it's defined this way, but I think that it's a little bit easier to see when you expand that out. So you can get, in this case, let's just pretend as though we had a 3x3 matrix. You get 3 linearly independent solutions to your homogeneous linear system. Okay, so these are not eigenvectors. Y sub 1, Y sub 2, and Y sub 3 as vectors are not eigenvectors. The only eigenvector that we got, honestly, was this guy right here, X sub 1. That's the only eigenvector we got. What we're going to do is use that eigenvector to generate other solutions, other linearly independent solutions to our original homogeneous system. The first solution will be just like we ran into in the previous section. We find our eigenvalue, which in this case is lambda. We find a corresponding eigenvector that we call x sub 1. And the solution that we get at first is just a vector x sub 1 e to the lambda t. Great. But again, let's pretend lambda has multiplicity 3 and it only generates 1 eigenvector. Okay, finding the next linearly independent solution, not the next eigenvector, but the next linearly independent solution. We're going to take that very same eigenvector, and then we're going to park a t next to it, and then e to the lambda t. Okay, so far, so good. We're just powering up by powers of t. In fact, that happens every single time. So for the third linearly independent solution, we have x sub 1, and now we have t powered up to the second power, divided by 2 factorial, technically, e to the lambda t. If we had another solution, so let's pretend as though that lambda was an eigenvalue of multiplicity 4, then the beginning of our next linearly independent solution to the homogeneous system would be x sub 1 as a vector, t cubed over 3 factorial, e to the lambda t. They all kind of have that pattern to start. And then you see that we need an x sub 2 and an x sub 3. And actually, in this case down here, if I had continued, I'd have an x sub 2 t squared over 2 factorial, e to the lambda t, and I'd have a plus x sub 3 t to the first over 1 factorial, e to the lambda t, and then finally I'd have an x sub 4 e to the lambda t. And I hope you get that idea. That little pattern continues. The question is, where do those x sub 2s and x sub 3s and x sub 4s come from? And they come from this little process right here. When you found x sub 1, it was because you solved a minus lambda I times x sub 1 is equal to 0. You solved that and found your eigenvector. This was using your eigenvalue from your characteristic equation. But once you get that, you can actually continue forward and say, well, what would this vector right here, x sub 2, be if instead of having 0 on the right-hand side, I have x sub 1 on the right-hand side? And then when you solve that, you get some vector we'll call x sub 2. And then you could do that again. You could say, well, what would that vector x sub 3 be if we replace the right-hand side with x sub 2? And we could continue on this way and say, okay, well, now if I want to find x sub 4, I'm just going to solve this is equal to x sub 3. It's a very, what we call an iterative scheme. Very, very neat little process. Of course, it does involve solving systems over and over again, but that generates our solutions, our linearly independent solutions to our homogeneous system where our eigenvalue, lambda, has multiplicity m, but it only generates one eigenvector. Now, I do want to mention something that I didn't cover in class because I just didn't want to, is that it should be a natural question that you have that, well, what if the eigenvalue lambda has multiplicity 10, let's just say, but it generates 2 different eigenvectors? Can I still use this process? And the answer to that question is sort of. It's actually a pretty ugly process, and it's not one you want to do, especially if you end up getting, let's just pretend, that eigenvalue of multiplicity 10, but it generates, let's just pretend, 5 linearly independent eigenvectors, but you still have 5 more to grab. That would be disastrously bad. So I really don't like to teach that method because that's like the worst case scenario. That's really a terrible scenario, and it takes quite some time to actually master. And if you look at both our textbook and the textbook that I used to use, there's like 2 problems in the entire textbook that use that method. So I'm not really super concerned about it. All right. Going on to our new material. So all of this time I was just prepping to get us up to speed. Now we're going to do the last case where we have an eigenvalue, but our eigenvalue is not real. So our eigenvalue is a complex value eigenvalue. And this is what I state here. We finally tackled the question, what if the eigenvalues are complex? And luckily, we've actually seen this case in the past. I'm going to go ahead and grab the ink down below and move this up. Now, I kind of like how the author does this, but I kind of don't. But I do kind of like it. I think he's really done a great job making it as succinct as possible, because this can be a little bit confusing, I think, for most people. But the way he approaches it, I kind of dig. So let's talk about this theorem right here. We're going to let A be a square matrix. Remember, every single time when you're dealing with systems of a homogeneous system of differential equations, you're always going to have a square matrix, period. Also suppose that the matrix itself has real entries. Complex valued entries are for a completely different course. Now suppose that lambda, which is equal to alpha plus I beta, where beta is non-zero, is a complex eigenvalue of A. One thing I want to mention before I continue this sentence. We know from the fundamental theorem of algebra, a theorem that roughly is around the time you learn the fundamental theorem of algebra, that complex roots to polynomial equations come in complex conjugate pairs. That is, if lambda is an eigenvalue, then so is alpha minus I beta. They're both going to be eigenvalues. However, what's beautiful about the way the author here does this topic is he just basically says, look, we know they come in complex conjugate pairs. Let's just focus on the one with the positive beta, which I really appreciate. It really does shrink this conversation down to its bare bones. The other thing we're going to state here, and this might throw you off because the sentence is really poorly designed, but we're going to let x, the vector x, in fact the eigenvector x, be the sum of two vectors, a u plus iv. The vector u is called the real part of the eigenvector, and the vector v is called the imaginary part. That should make sense. U and v both have real components because the I has been factored out of v. Now, it should make sense to you that if you have, maybe it's not that you can understand completely why it makes sense, but it should at least be somewhat convincing if I tell you I have a complex valued eigenvalue, that my eigenvector would probably have complex numbers in it as well. U and v, in this case, are going to both be non-zero. Why? Because if they're both zero, we don't have an eigenvector. Remember, eigenvectors have to be non-zero. So u and v are both non-zero. Okay, well, technically, you might think maybe u could be zero, but not the v. No, they are actually both non-zero. Then we get two linearly independent solutions, y sub 1 and y sub 2. Y sub 1 is going to be e to the alpha t. Now this should look familiar, what I'm about to say. If I said it was e to the alpha t and then I told you, but ignore the u and the v here. If I just said e to the alpha t cosine beta t minus or plus sine beta t, you would say, oh, yeah, that's very much like when we had imaginary solutions to second order differential equations from the past. And you're absolutely right, it is that. But we get these extra vectors in here because we're dealing with systems of equations, and so we need a list of solutions. So it's e to the alpha t times the quantity u cosine of beta t minus v sine of beta t. And then the second linearly independent solution is e to the alpha t times the quantity u sine of beta t plus v cosine beta t. Now, I used to make students memorize this in the past, and it's really kind of, if you have a good memory, it's pretty easy to memorize, but I love the way the author actually says this next part. These are actually just the real and imaginary parts of this right here. And if you don't believe me, you could multiply it out, actually. If you multiply this out, so all you need to know is, it's sort of like we got what we got earlier. We got e to the alpha t cosine beta t plus I sine beta t. And then, actually we didn't have the I in, well, we did have the I in there. And then multiplying by the eigenvector u plus iv. Now, if you distribute things through, now when I distributed that through, I kind of I paused halfway through or partway through because I really have a real bad habit of not being consistent where I place vectors. And remember, sine of beta t is just a constant, so I could place it on the right hand side or the left hand side of that vector, but notice all the other terms, I have my vectors on the right hand side. It's just a terrible habit I have. I apologize. Anyway, if you collect the terms that have I and collect the terms with only real parts to them, you get the following. And if you take a look at that, so the first piece, I'll highlight it right here, that is actually, if you take a look up here, that's just that guy right there. That's called the real part. And then the imaginary part is e to the alpha t, and then you can see it's u sine of beta t plus v cosine beta t. And that's all this stuff right there. So I actually kind of dig it that your author says, look, you just have a real part to this and an imaginary part to that. So it's very nice. It's that e to the alpha t cosine I sine business. And then we have the eigenvector itself, u plus iv. That's actually a really nice way to do it. And then if you need to know which part's real, just distribute very quickly and you can find out. Anyway, we get linearly independent solutions. Long-winded story is we have linearly independent solutions when you have a complex conjugate pair for an eigenvalue. Each of them generates linearly independent solutions. That's the punchline. So let's see it in an action. And because I'm recording this, I can kind of speed up my computations as I need. So we have part A here. I'll even rewrite that. And we're told that we need to solve this. And we now know that whenever we're asked to solve a homogeneous system of differential equations, we need to find eigenvalues and eigenvectors. So let's go ahead and find the eigenvalues. And that's found by taking a minus lambda I and finding the determinant of that. There we go. Let's go ahead and compute. Remember, it's the positive product of the main diagonal and minus the product of the off diagonal. We get down to that guy right there. And now some little distribution. Now we need to solve that quadratic equation, and you can see it doesn't factor very nicely. All right. Now, I usually do not like writing down like, okay, like when you're solving, for example, when you're teaching algebra, I hate when people do this. Oh, A is 1 and B is -4 and C is 13. I really dig that. I dislike that because it just is very algorithmic, and I like a very natural feel to mathematics. However, here, I actually break that rule for me, and I'm just going to make a little mention that we know the real part of our eigenvalue is 2, and the imaginary part of our eigenvalue is 3. This matches with the theorem that was listed up above. Let's just see it right here, that we have an eigenvalue alpha plus I beta. Notice I don't have the plus or minus because that doesn't actually matter. It didn't actually matter when we generated the solution, so don't really worry about the minus part. Just say alpha is 2, beta is 3. That's absolutely fine. All right, so what do we do with this? Now that we know our eigenvalues are 2 plus or minus 3i, it seems like we have to test both of them, but actually you don't. You only have to find the eigenvector for one of them, and then you have both. Again, that is the entire premise of that theorem, is that all you need is one of the complex conjugate eigenvalues, and it will generate 2 linearly independent solutions for you. So let's go ahead and do that. And it's generated off of only one eigenvector. Obviously, the other eigenvector is probably a u minus iv, but I don't really care about that. So let's go ahead and do this. If lambda is equal to 2 plus 3i, then to find the corresponding eigenvector, I'm going to have to plug that into that matrix up here. And I do have to solve the corresponding system, right? So we're going to take 5 minus that lambda, along with the -6 augmenting with 0, and then 3, and then -1 minus lambda augmenting with 0. And we're going to go ahead and plug that lambda in. Now remember, lambda is 2 plus 3i. So 5 minus 2 is going to be a 3. And we're subtracting the entire lambda, so it's minus 3i. And then we get here -1 minus the 2 is a -3. And then again, minus lambda means, or a negative lambda means you have a -3i. My guess here is that many people who are watching this, many of the students here, have not solved a system of equations involving complex values. And that's okay, because nor did I when I was a student. So my first piece of advice: divide rows by whatever common value they have. For example, that first row, I'm going to divide out 3. I'm going to divide row 1 by 3, and actually row 2 by 3. The next thing I'm going to do is I'm going to force this leading entry to be a real number. Now you may say, well, why don't you just swap rows 1 and 2? And I totally can. But I actually just have a habit of forcing whatever number I'm working with to be a real number. So what I'm going to do is multiply this entire row by the complex conjugate of 1 minus I. And that'll be 1 plus I. And yes, like I said, you could have swapped rows 1 and 2, but you still would have some complex conjugate work to deal with. So no matter what, you'd have to do what I'm doing right now. So I might as well just do it here. When you're multiplying a complex number by its conjugate, the result will be the first coefficient, or the real part, squared, plus the second coefficient, or the imaginary part, being squared. So this will be 1 plus 1, or 2. You can double check my work if you want to. Since I'm recording this, it doesn't take much for me to check it. So you can see the i's in the center cancel, but you have 1 minus a negative I squared, or 1 minus I squared, sorry. But I squared is a negative 1, and there you go. You get 1 plus 1 is 2. All right. Now remember, I'm multiplying everything by the complex conjugate. So the next will be negative 2, 1 plus I, and then finally 0. I'm going to divide, and I'll take the opposite of row 1 and add it to row 2 to become the new row 2. Or you could just easily say, look, row 1 and row 2 are the same. So I'll zero out row 2. That's another way you could say that, because they are the same. You say to yourself, great, I'm done, right? And I would say, yep, you're pretty close to being done, actually. So let's go ahead and write in here what x sub 1 is. We see that 1x sub 1 minus 1 plus I times x sub 2 should be 0. Remember, the leading entry associated with x sub 1 is non-zero, but x sub 2 does not have a leading entry in its column at all. So x sub 2 is free. I'm going to go ahead and solve this top equation for x sub 1 in terms of x sub 2. Remember, x sub 2 is free. I'm going to go ahead and allow x sub 2 to be 1. If you do that, you get the solution, or the eigenvector here, which I'll call x sub 1. Why not? It's the vector x sub 1. I do understand the notation is atrocious, but such is life. That's our eigenvector x sub 1 is equal to the entry x sub 1, entry x sub 2. But we know entry x sub 1 is 1 plus I times x sub 2, and we know x sub 2 is free, and so I'll let x sub 2 be 1. Now note, this eigenvector has a real part to it and an imaginary part to it. The real part is 1, 1. The imaginary part, which I'll write this way, is 1, 0. In other words, the first entry does have an I in it. The second entry has 0 of them. So in our formula that you would see up above, right, actually it's way over to the left here, we found our eigenvector. They called it x, which is perfectly fine. That's okay. But we've written it as u plus iv. Now I happen to know my solution without looking. I'm not going to look at the format they've provided. I just know that my solutions should be of the following form. Y is equal to, actually I'm not going to write y equals, I'm going to go ahead and write it this way. E to the alpha t, so I was going to say lambda, but it's e to the alpha t times the cosine of beta t plus I sine of beta t. Okay, so that's actually what we normally would have run into before as well when we did second order differential equations. And then we're multiplying this by the vector u plus iv. From this, I want to generate a real part and an imaginary part. So if you can see the distributions, you'll see that you get e to the alpha t. The real part is going to be cosine of beta t times u. And then the other part of the real part will be the I times I business, right? I squared is a negative 1, so it'll be minus. And then we have the sine of beta t. Oops, there's supposed to be a t there, times v. That's the real part of this. Now the stuff with the imaginary components, which I could just write as I e to the alpha t. So let's see, the imaginary parts come from this. I times v times cosine of beta t, so that's cosine beta t times v. And honestly, if it was me, I would generate it this way every single time, just out of habit. And then the other imaginary piece would be the sine plus the sine of beta t times u. These are both two linearly independent solutions to our homogeneous system. So I'll call that first one y sub 1, e to the alpha. Now I'm going to just look at what alpha and beta are. Remember, alpha is 2, beta is 3. Also remember, all the way over to the right, u is 1, 1, and v is 0, 1. Now, to be honest, nobody's going to write it like that. They're actually going to glue those two vectors together. So they're going to take this cosine of 3t and multiply it into this vector, which means you're multiplying both entries of the vector by cosine of 3t. Same thing with this sine of 3t. Move it into this vector, and then you'll take their difference. All right, so that's y sub 1. Y sub 2, on the other hand, just looking up at this business right here, and then doing the same thing we did before. There we go. Those are our two linearly independent solutions. They form a fundamental set of solutions for our solution space. That is, any solution is written as a linear combination of y sub 1 and y sub 2. Very nice. I know that it seems pretty complex, pun intended, but it's actually not too bad until you get to the 3x3. The 3x3 is a little nutty, which I'm happy to do. It's just that it's better to do in a video format like this. So let's take a look at the 3x3 there. And this one's nutty because the numbers are, the eigenvalues are just terrible. They're not fun. But let's go ahead and try it out. They're not terrible numbers, it's just hard to find them. So let's go ahead and do that. Now you can see that this is going to be a little bit of a disaster as we go through, but we have to do it. It's good practice. So let's go ahead and find the eigenvalues. We'll solve the following. And unfortunately, no matter how we expand this, it's just going to be just absolutely horrid. There's just not much I could say about that. I do look for kind of the worst looking column or row if I don't have a row of zeros. So I'll expand about this row right here. Remember, when you do that, start in the upper left-hand corner, plus, minus, plus, minus, plus. Here we go. All right, we get down to this. That's quite a bit of work, right? It's a lot of work for this one right here. It's not really conducive for making you feel confident. And then we want to solve this polynomial equals 0. Probably the best thing to do is multiply everything by -1 first. And then use the rational roots theorem to try to find a root of this. Now we know plus or minus 1, plus or minus 2. Let's see, plus or minus 2, 13. And plus or minus 26. Those are only possible rational roots. So trying 1, we can see that that does not work. So erase that work and try -1. Again, you see that does not work either. So let's go ahead and erase that again. Now we'll try 2. And I'll erase these roots as I try them, by the way. You can see that doesn't work as well. So man, we're really not batting 1,000 here. Or maybe we are batting 1,000 because we're very consistent about not finding a rational root. Let's go ahead and try -2. There we go. We found it. So now we know that -2 is a root of that polynomial. That is lambda minus a -2. In other words, lambda plus 2 is a factor. And what remains after factoring out lambda plus 2 is a lambda squared, 1 lambda squared technically, minus 4 lambda plus 13. Gosh, that looks hauntingly familiar. Let's see. Was that from the previous problem? That'd be great if it was. Look at that. I think that's pretty good. I think. Yep, very same exact factorization. So there we go. That's kind of nice, although totally different matrix that we're dealing with here. So the eigenvectors associated with that are going to be different, but at least I know the roots that immediately are 2 and 3. So our eigenvalues are lambda equals -2, and then lambda equals 2 plus or minus 3i. Again, we know it's 2 plus or minus 3i because we saw this guy before. This is just by happy accident. Now our goal, honestly, is to solve this homogeneous system. So we found one real eigenvalue. Let's go ahead and find the eigenvector associated with that one real eigenvalue. So I'm going to plug in to a minus lambda I. I'm going to plug in lambda equals a -2. Let me go ahead and do that. Before I go diving into this, I just want to make sure you understand that what I did is I took, actually you can kind of look at it right here. I took that and let lambda equal -2. So 3 minus -2 is 5, 7 minus -2 is 9, and -8 minus -2 is -6. Every other entry is the same. And then I just go through and I solve this system. Note rows 2 and 3 are identical, so I can zero out that bottom row. Simultaneously, I'm going to go ahead and divide that second row by 5. And it is to your benefit when you're doing the row reduction or getting to a row echelon form here, that you go ahead and use this entry to kill up above as well. Trust me, it's a great idea. So I'm going to take 4 times row 2 and add it to row 1. And I might as well just do it, dividing row 1 by 5. And as equations, this tells me x sub 1 minus 2x sub 3 is equal to 0. And x sub 2 minus 2x sub 3 is equal to 0. The only variable without a leading coefficient, or basically the only variable that doesn't have a lead entry in its column, is the x sub 3 variable. So x sub 3 is free. So when we get here, we just say, we know that our eigenvector, our first eigenvector, is going to be, and here I'm just going to go ahead and just say, let x sub 3 be 1. So x sub 1 is twice 1, x sub 2 is twice 1, and x sub 3 is 1. So there we go. That's our eigenvector associated with the eigenvalue of, what was it, a -2? Yeah. So I happen to know one of my solutions. I'll write my solutions in blue here. I know the first solution is going to be e to the eigenvalue, t, times the vector that we just found, the eigenvector. In fact, we normally write it the other way, don't we? So let's go. Well, no, we write it that way. That's fine. So that one's done. And we now have the painful part of finding the eigenvector, and therefore the linearly independent solutions associated with the complex conjugate pair of solutions. So, or of eigenvalues. So what we're going to do is, again, take a snapshot of that, and I'll actually just copy it down here very quickly. And note, I am writing alpha equals 2 and beta equals 3 because the real part is 2 and the imaginary part is 3. Now I'm going to substitute in the lambda there. So remember, you're subtracting that entire lambda. So you will, all those that middle diagonal there, the main diagonal, will all have a -3i on it. The terrible thing about this is that if you look through each row, there's nothing that you can divide out of each row. That's you can't divide row 1 by 2, for example. You get fractions. You don't want to do that. So, such is life. I'm going to start the same way I did before, which is I'm going to multiply this top row by the conjugate, the complex conjugate of that leading entry. So I'm going to multiply by 1 plus 3i. Remember, when we do that, this will become 1 plus 9, or 10. Notice what I did, or what I'm doing here, other than the ink. I just wanted the ink to be thicker. But notice what I'm doing here. I am not distributing out these constants through these parentheses. It's for a very special reason, because note in that first row, everything is divisible by 2. And I could still probably see that, obviously, but it's just much easier to see when you're not actually, multiplying those through. So I'm going to go ahead and divide that first row by 2. And here comes the fun part. When I say fun, I mean not so fun. So it's probably best at this point, since we've already cleaned up that top row, to distribute that -2 through. I know that I'm not going to need to do anything else with that top row, so I'm going to distribute this -2 through. I'll get a -2 minus 6i here, and I'll get a -1 minus 3i there. Now I'm going to just add rows 1 and 2 to become the new row 2. Now you can see I've actually gone pretty far to the right on my page, so I'm going to continue it right here. Now, as you see, there is going to be a lot of room for mistakes here. Just watch your arithmetic. That's the best thing I could possibly tell you, is watch your arithmetic. There's going to be a lot of possibility for arithmetic mistakes. Now I'm going to take that first row and I'm going to multiply everything in it by 2. So I'm just going to pre-multiply so that I have that in front of me. So when I multiply that row by 2, I'll get a 10, a -4 minus 12i, and I'll get a -2 minus 6i. And I'm going to add that down to the third row. I just did that pre-multiplication, so it's a little bit easier for me to see. Okay. Now, at this point, be very aware those second and third rows are both divisible by 3, so I'm just going to quickly do that. All right, now I'm going to do the same thing I've been doing. These lead elements, actually both of them, these lead entries, I'm going to multiply each row by the conjugate of those entries. Again, lots of room for arithmetic mistakes. The reason why I'm doing this is just because, trust me, it's much easier to do it this way. All right, so let's see, this first entry times its conjugate will be 1 plus 9, or 10. The next entry right here times that 1 plus 3i, that I'm going to do off to the side. That's kind of nice. It comes out to be a -10i, which is very attractive. I hope you can see that. In fact, I'm going to go ahead and divide that entire row by 10 right now. All right, let's deal with the third row. I'm going to tell you that third row is exactly the second row, but you're probably not able to see it right now, so let's just go ahead and do it. Multiplying 3 minus 4i times 3 plus 4i, I will get 9 plus 16, which is 25. And then finally, multiplying this by 3 plus 4i, let's go ahead and do it. And again, we get this beautiful -25i, and I could divide that entire row by 25. And you see it's identical to the row above, so I can zero it out. And the last little move I'm going to make, honestly, is the one where I use this entry to kill up above. So I'm going to multiply row 2 by 2 plus 6i, and I'm going to add it to row 1. Now, again, multiplying this entry right here by 2 plus 6i gives me 2 plus 6i, and I add it to -2 minus 6i, that'll give me a 0 by design. Multiplying this by 2 plus 6i, I will get a -2i plus 6i times a -i, but a I squared is a -1, so I get a 6 minus 2i. Now 6 minus 2i plus what we get up above, add those together, we get this beautiful 5 minus 5i, and you can see I can divide that top row by 5. And you can see why this would just melt your brain in class. It's hard enough to watch right now, I'm sure. But at least we get down to this, that x sub 1 plus 1 minus I times x sub 3 is equal to 0. And x sub 2 minus I x sub 3 is equal to 0. Notice the only variable without a leading entry in its column is x sub 3. So x sub 3 is free. Cleaning this up just a little bit, and I'll go ahead and just choose x sub 3 to be 1, just because I can. And so we get the an eigenvector for this to be the following. Splitting that into two pieces, one that contains only the real numbers and the other one being the coefficients of the imaginary numbers, you get the following. This will be my vector u, this will be my vector v. And if you remember, if your brain is still somehow functioning after all that, you happen to know that the two linearly independent solutions you're going to get for this complex conjugate eigenvalue, they're going to be of the form e to the alpha, which alpha here is 2, t, times the quantity cosine of beta t plus I sine of beta t, and that's going to be times the vector u plus I times the vector v. And what we're going to do is distribute through and collect the real and imaginary parts. The real parts I'm going to throw into the first linearly independent solution, and the imaginary parts I'll put into the second linearly independent solution. Just as an aside, very quickly, is that we've already labeled one of our solutions y sub 1. So these will be labeled y sub 2 and y sub 3. All right, so there is our real part. U again was -1, 0, 1. V was 1, 1, 0. So let me just go ahead and use those here. Again, U was -1, 0, 1. And V was 1, 1, 0. All right, now for our last solution. And this one is going to be the imaginary parts, right? So we're going to have these two right here and these two right here, basically. Without the I, by the way. This will not have the I involved, so you're not going to keep the I on that. That's just a constant, and we know we're going to bleed that constant into the C sub 3 that we're eventually going to throw on the front of that. All right, so again, U is, let's see, I'm just looking at my screen here, -1, 0, 1. So it'd be negative sine of 3t space sine of 3t. And V is 1, 1, 0, so that's a positive 1 times the cosine of 3t. Next line down is a positive 1 times the cosine of 3t. And the last line will have 0 of anything, basically. And so there we go. There's our two linearly independent vector solutions for our complex conjugate eigenvalues for our matrix A. And then the final answer is the vector that is the linear combination of y1, y2, and y3. I actually prefer to do this in a lecture video than live because, again, this is mind numbing. All right, so that's it. We're done. All right. Note, this is pretty algorithmic. It's not too bad. I'm cheering you on. I think you guys could do it. You guys have done a phenomenal job throughout the course so far. So just kick butt at the very end. All right. Okay. I will see you all on Monday.